Thank you very much. It's very nice to be here. Can you all hear me okay? Okay, great. Well, it's a great pleasure to see you all here. It's a sort of pleasure for me to come back for the day and see Cambridge again. So about 100 years ago, when I was your age, I was preparing for STEP. And I just kind of wanted to reassure you that it's possible to do things like STEP and MAT and come out the other side. I found the questions I was doing really hard. There wasn't anybody in my sixth form college who'd done STEP recently, so the teachers hadn't sort of done the questions and so on. I was kind of doing it by myself. They were really hard questions. I really enjoyed the challenge. When I practiced, I got better at doing them. So that's my tip for you. I'm supposed to tell you about how to solve equations. I kind of wish I knew how to solve equations. Solving equations is quite hard, but let's see how we go. So what I thought I'd do is give you some equations, and I don't want you to try to solve them. I just want you to look at them and get a sense of how many solutions you think they have. And talk to your neighbour, spend a minute. So this isn't get your pens and paper out. I don't want you to spend lots of time solving the equations. Just use your instincts, which is a kind of way of saying your experience, your intuition, your feeling for how many solutions each of these equations should have, okay? So if you don't know the person next to you, well, just be brave and talk to them anyway, okay? And we'll have a vote in a moment. So here are the equations, okay? And this isn't supposed to be easy, right? I don't do easy problems. And it's multiple choice, okay? So you can tell me there are no solutions, one solution, two solutions, three or more solutions, but a finite number, or infinitely many solutions. Okay, so take a minute, talk to your neighbour. How many solutions? What a fantastic buzz of mathematical chatter. Okay, so I'm rudely going to interrupt you. I don't mind if you don't definitely know the answer, okay? This isn't about definitely knowing the answer. This is just about what's your feeling for it, what's your intuition. So let's do a vote, right? You've had a chance to talk to your neighbour. Hopefully that means voting is a little bit less scary. And I promise there are no consequences, okay? I'm not going to pick on you, whatever you vote, so you can be brave. So the first one, x squared plus 2 equals 0. Who votes for no solutions? A few people. Be bold, okay? Be bold. Great. Who votes for one solution? Okay, two solutions. Interesting. Three or more but finitely many? Infinitely many? Okay. So maths isn't a democracy, right? I mean, you vote something that doesn't change. That doesn't make it whatever it is. But that's really interesting. Okay. What about the next one? 2 over x plus 3 over y equals 1 over 6. Who votes for no solutions? One solution? Okay, so there's some hands up. This is good. Two solutions. Slightly more. Three or more solutions. Infinitely many solutions? Okay, so there's quite a lot of undecideds there. X to the 17 plus y to the 17 equals z to the 17. No solutions? A few people. One solution? Two? Three or more? Infinitely many? Okay, this is good. What about the last one? Y squared is x cubed minus 2. Who votes for no solutions? One solution? Two solutions? Few hands up. 3 or more? Quite a lot? Infinitely many? Okay. So what I'm learning from this is that you do have a feeling for some of these problems, kind of what it might be, but actually they're quite hard equations. So some of them you're looking at and you don't automatically. So I think people felt much happier with the first one maybe than the later ones. That's my impression. There's a bit of me that thinks this was kind of an unfair question because it matters quite a lot what kind of solutions we're looking for, right? So there's lots of people thinking, yeah, that's what I thought. Why didn't she say that before? Well, in a parallel universe, there's a version of this slide that asks about integer solutions, for example. Whole number. Am I allowed to use the word integer? Integer just means whole number. Positive, 0, negative. They're all integers. So some of you might think, oh, well, if she said integer, I'd have changed my answer. Some of you might have been thinking about integers all along. So yeah, we have to be precise, I guess. So basically, I'm just sort of planning to tell you a bit about each of these 4 equations. And I'm particularly interested in integer solutions. So Julia mentioned I wanted to talk about some number theory. Number theory is all about properties of whole numbers. It's a part of maths that I find particularly interesting. But along the way, I'll mention some of the other kinds of places we might look for solutions as well. So x squared plus 2 equals 0. So I guess that has no integer solutions. Because if I take any whole number and square it, I get something that's greater than or equal to 0. If I add 2, I definitely don't get a 0. And in fact, there are no rational solutions. Am I allowed to talk about rational numbers? Rational numbers means fractions. So a ratio of one whole number divided by another, just not dividing by 0. Why does it have no rational solutions? Well, exactly the same reason it had no integer solutions, right? In fact, it's got no real solutions. And some of you said, well, this equation's got no solutions. And you might have been thinking about integers, you might have been thinking about real numbers. But if we extend the pool of numbers that we're working with, if we allow ourselves to use complex numbers as well, then we find that it's got 2 solutions. And maybe I can deduce how many of you in the room have started thinking about complex numbers by how many of you said, oh, it's got 2 solutions. So the answers depend crucially on where we're working. And this sort of mirrors the kind of historical sort of, as mathematicians have evolved our study of equations, we've wanted to introduce new kinds of numbers to allow ourselves to solve more and more equations. So complex numbers became crucial when we realized we just needed to be able to solve more kinds of equations than we were currently able to deal with. So, good. Let's talk about this equation, which started to cause a few more difficulties, I think. So one thing we might try to do, I guess is often quite helpful when we think about solutions, is to draw a graph. Yeah? So I hope you're all good at sketching graphs. I really recommend being good at sketching graphs. But I'm not very good at sketching graphs on my computer, so I got a website to draw it for me. So what this is showing is that there are lots of pairs x and y that satisfy this equation. But the graph is just thinking about real numbers that satisfy. And I'm interested in whole numbers that satisfy. It's very hard to tell, looking at a graph like this, about whole number solutions to this equation. So let's do something sort of slightly different. So there are lots and lots of pairs x, y that satisfy this. But it's not quite sort of obvious to me when I look at this equation. How am I supposed to know how many integer solutions it has, how many whole numbers? It's kind of a very odd-looking equation. Well, let's make it look less odd. I'm interested in whole numbers, and this is, I mean, one of the things I find difficult about this is it's got all these kind of denominators, and x and y are on the bottom and stuff. It's sort of horrible. So let's multiply through, and it's really nerve-wracking having like algebra on my slides, because the chances of my having made a mistake are quite high. But I think I've multiplied everything in sight by 6xy to clear the denominators. And what I like about this equation is there are no kind of fraction-y type things, right? Everything in sight is a whole number. I feel much happier in the world of whole numbers. And I can shove everything across to one side because it's nice to have 0 on the right-hand side or something. There's a bit of me that sort of thinks I should have given you half an hour to think about this problem, but then I wouldn't have been able to tell you so much stuff. So I'm just going to keep pressing on. So looking at this equation, I think, well, how are we going to figure out which x and y satisfy this equation? I don't know about you, but I look at this left-hand side, and I sort of want to try to factorize. Is factorizing a good way of solving equations, right? So things are equal to 0, and you sort of factorize and quadratics and things. So we could try to factorize the left-hand side. And what I've done here is I've just kind of guessed what the brackets ought to be. This is a really powerful, guessing is a really good thing to do. So I've got xy here. This is giving me my minus 12y. This is giving me my minus 18x. So this is all good. But I get another term from these brackets as well, right? I get plus 12 times 18. So all I'm going to do is write down on the right-hand side whatever I need to write down to make this a true equation, which is 12 times 18. And I really love number theory, and I really don't love arithmetic, so I couldn't be bothered to work out what 12 times 18 is. So I'll just leave it as 12 times 18. Because actually, I'm kind of thinking ahead to the next step. I mean, well, how is this going to help me? Because normally, I factorize, and then I know one of the factors must be 0 because the product's 0, that kind of thing. I'm sort of looking in case any of you are going to nod as though you know what I'm talking about. Yeah, there's some nods, thank you. But I haven't got 0 on the right-hand side here, so I have to be really careful. But here's where it really matters that we're looking for x and y to be whole numbers, right? Because it means that x minus 12 and y minus 18 have to be whole numbers. So they have to be factors of the thing on the right. And that's kind of why I didn't bother to work out what 12 times 18 is, because if I'm just thinking about factors, I may as well leave it like that. So what we discover is that x minus 12 has to be a factor of 12 times 18, and then y minus 18 has to be whatever the factor is to complete that product. Actually, I sort of feel like I've morally solved the problem now. This is a classic mathematician. I don't care what the solutions are. I don't actually care how many of them are. I feel completely confident that if you locked me in a room for 5 minutes and said you're not coming out until you've written a list of the solutions, that I'd be able to do it, right? Because I'd write a list of the factors of 12 times 18. I'd carefully remember there are some negative factors of 12 times 18. And then I just work out what the corresponding x's and y's are. So I sort of feel like I've basically finished at this point. So let's not write a long list of factors because nobody cares. But I guess the message here is there are going to be quite a lot of solutions. But even though we've got 2 variables and just 1 equation, we've got this extra piece of information that we're looking for whole number solutions. So normally we'd have kind of infinitely many because we saw that real graph. But the extra information that we're only looking for whole number solutions narrows that down. I find that kind of intriguing. I quite like this kind of argument where we really exploit the fact that we're looking for whole number solutions. And you could sort of stare at the equation and maybe guess, happen to stumble across, get lucky, find some solutions. But actually being clear that we've got all of them, I really like this. If you like this kind of problem, I thought we'd have a little advert break. Okay, this is the time for the advert break. So don't leave the room to make a cup of tea. Don't get your popcorn out. Here's the advert break. So maybe some of you have heard of the UK Maths Trust, who organise maths challenges and team maths challenges and that kind of thing. And UKMT organises a mathematical Olympiad for girls, the UK MOG. And in 2016, it's going to be on that date. And if you look at this website, you can find some past papers and see the kinds of things. So the way this works is that UKMT sends some teams to international maths competitions each year, including the European Girls Maths Olympiad, which in fact UKMT was involved in setting up a few years ago. And this is the beginning of the talent search to sort of encourage girls to get involved, join in with the mentoring program. We have sort of training, practice problem solving, and then potentially be picked for a team to go and represent the UK. So this year's UK team have just got back from the European Girls Maths Olympiad in Romania and have come back with a gold medal, a silver medal, and 2 bronze medals, which is the best ever team performance. So we're all very excited. And if you like solving really hard maths problems, then this is the thing for you. Right, let's go back to solving hard maths problems. Here's an equation. This is quite a hard equation. I mean, where do you even start? And I just picked a number 17 because I like it, basically. So let's have a warm-up problem. Right? This is a really good thing to do when you're stuck on a problem. Just pick an easier problem and do that instead. It's a really good thing to do. It's what professional mathematicians do all the time. So I thought we might think about this problem instead. X squared plus y squared equals z squared. Anyone recognize this equation? A few people? Yeah, Pythagoras. So if I've got a right-angled triangle with sides x and y, the hypotenuse z, they satisfy this relationship. And maybe you know some integer right-angled triangles, because maths textbooks like them, maths teachers like them, right? They're sort of learning about Pythagoras' theorem. It's really nice to be able to practice applying it and find some triangles that have whole number answers. We have a name for these. These are called Pythagorean triples. So if you've got x, y, and z that satisfy this equation, it's called Pythagorean triples. So maybe you've seen 3, 4, 5s, very famous. So there's a right-angled triangle with sides 3, 4, 5. And then you can see 3 squared, I guess that's 9, plus 4 squared, that's 16. That's 25, which is 5 squared. So it satisfies this equation. 5, 12, 13 is another favourite of the textbooks. There are, you sort of play around. You can find examples of these things. So for me, one of these stands out as being much less interesting than the others. So I thought I'd give you 20 seconds to talk to your neighbour to discuss whether you think one of these is less interesting or whether they're all as interesting as each other. Talk to your neighbour, see what you think. So I don't think I'm cheating here. I think these are all genuinely Pythagorean triples. So it's not that. But who thinks they're all as interesting as each other? Who thinks one of them is less interesting? Few people. OK, which one do you think is less interesting? Who thinks the top one is least interesting? Second one? Third one? Fourth one? Interesting. So I think the greatest number of hands was for the third one. Is somebody brave enough to say why they think the third one is least interesting? Yeah?
I don't know, this might be a coincidence, but it's got the same difference between the numbers.
The same difference between the numbers? So you mean this difference is 6 and this is 6? Yeah, interesting. Yeah? Is it 6 times the first one? So you mean this 18 is 6 times 3, 24 is 6 times 4, 30 is 6 times 5, which is in fact related to you've noticed the same thing in a different way. Yeah, so this one is somehow 6 times this one. If you imagine that triangle, that's like measuring your triangle with a ruler with different units or something, or blowing up your triangle. It's the same sort of proportions of triangles. And the reason that's relevant, so I'm really pleased you spotted that, that's great. The reason that's relevant is if I gave you this multiple choice question about how many integer solutions there are to this equation, well, the answer is definitely 3 or more, because here are 4. But there's a silly reason why the answer is infinitely many, which is I could just pick that 3, 4, 5 one and just multiply it up, scale it up by whatever I like. So there are infinitely many solutions for a sort of rubbish reason. So a more interesting question is, are there infinitely many genuinely different solutions, like genuinely different shaped triangles, not just the same thing scaled up over and over again? Now, how much do I want to give away here? Because you can think about this problem for yourselves, right? This is a problem that is within your reach. If you've got a bus journey back this evening, you can think about this. So maybe I will tell you that there are infinitely many genuinely different solutions. And there's a really beautiful way of describing them all. So you sort of give a kind of formula, a recipe for constructing them all. So if you think really carefully about this, this is really lovely. This goes right back to the ancient Greeks. So there's a chap called Diophantus who wrote a number theory textbook called the Arithmetica. And he described how to find all of these infinitely many genuinely different Pythagorean triples. And a lot of centuries later, like my precise grasp of counting decades, centuries there, somebody else came along and said, well, this is very interesting. I'm reading Diophantus's book. What if I change the power? What if instead of thinking about x squared plus y squared equals z squared, if I just forget about right-angled triangles a bit, what if I make it x cubed plus y cubed equals z cubed, or x to the power 17 plus y to the power 17 equals z to the power 17? How many solutions then? And presumably he went away and did some doodling on the back of an envelope or something. We don't know. Solutions. He somehow convinced himself positive whole numbers, so for powers greater than or equal to 3, there are no... So I have to say positive integers here because there are sort of silly solutions where one of the variables is 0. You know, if I have 3 cubed and minus 3 cubed, they add to give 0 cubed, that kind of thing. So you sort of rule out the uninteresting solutions. There are no interesting solutions with positive whole numbers. So Fermat was this French mathematician. His job wasn't a mathematician. He was a civil servant. He was a lawyer. He did maths in his spare time, as you do. And he was reading this ancient Greek textbook, and he was thinking, oh, this is really cool. And it was just his textbook. He was just doodling in the margin, and he wrote in the margin, there are no solutions to this equation. And I have a truly marvelous proof of this, which the margin is too small to contain. Don't write this in your maths homework. It goes down really badly with maths teachers. So he was just writing this for his own benefit. But after he died, his son published this textbook with all of his father's kind of scribblings in. He'd written all sorts of things. Fermat was really interested in understanding the number theory that the Greeks had done, but then taking it further, seeing what else he could do. What equations can I solve? What can I understand better than the Greeks? Can I add to what they did? Oh. Let's try again. I love blackboards. They never do that to you. Where was I? Fermat. So he had all these various assertions, and Fermat was really shocking at writing down his working. He just basically didn't bother. So after his death, his son published his book, and other people had to come along and try to check, was Fermat right or not? And sometimes he was, and other people were able to fill in the proofs, and sometimes he was wrong. He made mistakes. This is called Fermat's last theorem here. I can explain 2/3 of the name, okay? I can explain Fermat, because Fermat wrote it down in his textbook. I can explain last, because it was the last one of these claims that Fermat made that mathematicians hadn't decided one way or the other. I can't explain the theorem bit because he didn't have a proof. So it really shouldn't have been called a theorem. Claiming to have a proof is no good. You actually have to have one. And people spent a long time trying to figure out, is this a true statement or not? Can we prove this? Can we show that this is really the case? So Fermat himself, in fact, on one of the rare occasions when he did show his working, showed this result for the case n is 4. So he showed there are no positive whole number solutions to the equation x to the power 4 plus y to the power 4 equals z to the power 4. He did genuinely do that, which is part of the reason why I think maybe he even realized he'd made a mistake when he claimed to have done this, because if you claim to have proved it for all of these, why would you go back and do that special case later? Euler dealt with the case of the cubes a few years later. The first person to deal with a whole bunch of cases all at once was Sophie Germain. I'm sorry this is not a great picture. The quality of the digital cameras in the period she was alive didn't have very high resolution. Sophie Germain is a really interesting person. So she lived in Paris at an incredibly exciting time. They were building this fantastic university just down the road from her. It was a really exciting moment, except women weren't allowed to study there, which is just completely shocking, but it was a long time ago. Sophie Germain was a very determined individual. She really wanted to study maths. Her parents hadn't been so keen on this, so she used to lie there under the bedclothes with a candle doing maths. Please don't do this at home. So she somehow managed to get hold of the lecture notes from this fantastic university just down the road. And she was reading about what people were doing, and she was studying. And like Fermat, she wanted to take it further. She wasn't satisfied with reading what other people had done. She wanted to contribute her own work to it. And she worked on various things. So she worked on trying to develop a mathematical theory of elasticity, which was one of the kind of really exciting scientific problems of the time. She did a lot of work on number theory. So she read this book by Gauss, one of the greatest mathematicians of all time. It's a fantastic number theory book. And she really understood what this was about, and she was adding her own ideas, and she was thinking about Fermat's equation. And she wanted to write to Gauss and say, well, look, Mr. Gauss, this is what I'm working on. What do you think? She was worried that Gauss would not take her seriously if she wrote as Sophie Germain. So she pretended to be a bloke. She signed her letter Monsieur Leblanc. And she had this pseudonym, and they corresponded. And Gauss thought what a great mathematician Monsieur Leblanc was. He did eventually discover that Monsieur Leblanc was in fact Sophie Germain, to his credit, he thought that was great. He didn't think, oh, she's a woman. So Sophie Germain was somebody who was able to deal with a whole bunch of cases of Fermat's last theorem all at once. So Fermat had done fourth powers, Euler had done cubes. That's great, but if you just pick them off one at a time, it's going to take a long time because there are infinitely many cases to deal with. Sophie Germain was able to deal with a whole family of them, which was really exciting. And then others came along after that, building on her work. And it was finally solved in 1990s. It took a long time. So this is Andrew Wiles, kind of as he is now. He had a little bit more hair in 1995. So he was then in Princeton. He's now in Oxford. So the building I work in, the equivalent of the Centre for Mathematical Sciences here, is called the Andrew Wiles Building in Oxford. And his office is near mine. I haven't quite plucked up the courage to ask him how he feels about getting post addressed to Professor Sir Andrew Wiles, the Andrew Wiles Building. It's one of the most celebrated mathematical achievements of all time. It's such a famous problem, but the way he did it is just utterly beyond anything that Fermat could have begun to imagine. So what Andrew did was he proved a particular case of a result called the Taniyama-Shimura conjecture, and he had some help from his graduate student, then graduate student, former graduate student Richard Taylor. And they proved this particular result that somebody else had shown. Well, if that result's true, then Fermat's last theorem would also be true. So that was a really big motivation for Andrew Wiles to be working on this problem. He spent 7 years working on this problem. I just want you to put in context, maybe you were working on some hard problems today. Maybe you spent like half an hour being stuck or something. Maybe if you have a particularly kind teacher, they might sometimes give you a really hard problem and you might go away and be stuck on it for a week or something. I spent 4 years proving a result for my PhD, and that was like a tiny result, not like this kind of result. Andrew Wiles spent 7 years proving Fermat's last theorem. It's a pretty amazing achievement. Most people kind of talk to each other about what they're doing, so lots of mathematicians will collaborate and share ideas and so on. Andrew was really focused on, I'm just going to prove Fermat's last theorem. It's a really extraordinary. So there's this fantastic BBC Horizon documentary. If you haven't watched it, you are obliged to go and watch it. So you Google iPlayer Fermat's last theorem. So the documentary was made at the time, which is a long time ago by your standards. It's quite a long time ago by my standards. But it's online. It's on the iPlayer, and the best ever Horizon documentaries or something. It's fantastic. It is less than an hour of your life, and it's superb. Good. So what this means is that if I'm looking for positive integer solutions, the equation I gave you has no solutions. There are some boring solutions if you allow 0. OK, good. Let's go to the fourth equation I gave you. Y squared is x cubed minus 2. Yeah, so I guess this is third-year undergraduate material, but you won't mind if I carry on with this? Excellent. I like a bit of ambition. So if we just switch it round, it's like, so I've deliberately written this as y squared equals x cubed minus 2, and I'll try to remember to tell you why in a minute. But if we switch it round, it's just slightly easier to think about. So just think about cases. So if y is even, then y squared is even. So y squared plus 2 is even. So x cubed is even. So x is even. Great. Actually, if we think about this, if x is even, then x cubed is a multiple of 8. 2 times something times 2 times something times 2 times something, multiple of 8. But y squared plus 2 is not a multiple of 8. Y squared is a multiple of 4. I add 2. I don't get a multiple of 8. Don't worry if you're not getting all the details here. I just want to give you a kind of taste of it. So what we've said is if y is even, then we kind of discover that x and y, that they don't satisfy this equation. So if we've got a solution to this equation, then y has to be odd. That's great. So we started out with infinitely many possible values of y. And now we've got half of them. So that's still infinitely many possible values of y. Great. Yeah, that's sort of exhausted that line of thought. solving equations is really hard, and sometimes you need lots of ideas, and sometimes you try this idea and it doesn't seem so helpful, and then you have to have another idea, and you just kind of have to be fearless about trying it. I mean, if you sit there and think, oh gosh, I've got no idea at all how to solve this equation, you are guaranteed not to solve it. Whereas if you think, well, there's 0.5% chance that this idea might work, well, that's already a lot of progress, right? You may as well try it and see what happens. Okay, here's another idea. So if I look at this x cubed is y squared plus 2, so the right-hand side is a difference of 2 squares, so I could factorize that. It is just possible that you are not looking at this and thinking, oh yes, y squared plus 2, that's a difference of 2 squares. Partly because it's not a difference, and partly because they're not squares. But I say be more open-minded. Because if I thought about this as y squared minus minus 2, and I thought that minus 2 was a square, it would be a difference of 2 squares, right? I mean, what's not to like? This is how you make progress in mathematics, by just kind of thinking, well, what if? I'll give it a go. So here we go. I factorized it as a difference of 2 squares. So I've written this thing called square root of minus 2, and my estimate from thinking about x squared plus 2 equals 0 earlier on is that maybe a third of you haven't learnt about complex numbers yet and are thinking that's illegal. Well, that's okay. It'll all be fine, okay? So the square root of minus 2, here's what you need to know about the square root of minus 2, okay? If you square it, you get minus 2. I mean, if I give you the number square root of 2, what do you need to know about the square root of 2? You need to know that if you square it, you get 2. I don't see why the square root of 2 is somehow more superior than the square root of minus 2, just because I can put it on some number line somewhere. You know, big deal. I'm just going to write the square root of minus 2. So if you know about complex numbers, you might be thinking, oh, that's I times the square root of 2. That would be fine. The sort of convention in this area of number theory is not to write I, it's to write the square root of minus 2. So what I'm doing here is kind of conventional, but you could write it in terms of I. These are just complex numbers. And what I'm going to do is allow myself to work in this extended pool of numbers where instead of just having whole numbers, I'm allowed whole number plus whole number times the square root of minus 2. It's a little bit like real and imaginary parts for those of you who come across complex numbers. If you haven't come across complex numbers, don't panic. It'll all be fine. Just every time you see root minus 2 squared, we'll replace it by minus 2. So good, we've factorized this equation. Now I'm going to not fill in the details of a step for you because it's just a little bit fiddly and I don't want to spend time on it, but you can think about this. So I claim that the two factors on the right have highest common factor 1. So if you have something that divides into both of them, it has to be like 1 or minus 1. And I'll let you think about that. What's really powerful about that, that incidentally uses the fact that y is odd. So that little bit of working we did on the previous slide, where we pointlessly ruled out half the cases, actually turns out to be really helpful, because knowing that y is odd is useful in this stage of the argument. So now what we've got is two numbers that kind of have no factors in common, apart from 1 and minus 1, and their product is a cube. What that means is that each of these numbers individually must be a cube. Okay, this is hard, right? I told you, it's third-year undergraduate stuff, but I figured you'd like a challenge. So each of these is a cube. So for example, I can write y plus the square root of 2 as the cube of some number in this extended pool of numbers I'm using. So a and b are whole numbers here. This is just an arbitrary number in this pool of numbers I'm using, and y plus root minus 2 is equal to the cube of it. So I guess you're better at the binomial theorem than I am, so we can expand this thing out. Ta-da! So it looks a bit messy. Oh, look here. Here's a square root of minus 2 squared. So we can replace that by minus 2. And there's one in here we can simplify as well. So if I tidy that up, I've got these two terms which are just whole numbers. So that's this term, and then this part which is something times the square root of minus 2. Where is all this going? Don't know. I mean, basically, this was sort of doing this because I couldn't think of any other ideas, and we might as well try it, right? But actually, this is quite interesting, because what we know is that the coefficient of root minus 2 is 1. So this lot must be equal to 1. So for those of you who know about these things, this is like comparing real and imaginary parts. That's the idea. And I've sneakily factored out this b here. And now we can recycle an idea we had earlier. Mathematicians do this all the time, right? It's good for the environment. It saves having new ideas if you just recycle them. So earlier on, we had that x minus 12 and y minus 18 or whatever it was is equal to something. We said, well, that means x minus 12 had to be a factor of 12 times 18. Well, here, b times some other whole number has to be 1. And there are very few ways to get a 1 as a product of two whole numbers, right? So b has to be plus or minus 1, and then you can solve this has to be plus or minus 1, and you just figure out an a has to be plus or minus 1. And now we're pretty much done. So y here is this, if you like, the real part. We can substitute in a and b, and we get what y is. And then we can go back and figure out what x is. So you might have spotted from this equation that 25 is a square number is 27 cube number minus 2, which would give us these two solutions, 3 and plus or minus 5. What's great about this is it shows they're the only solutions. Along the way, we've done some fairly sophisticated algebraic number theory, but it's good to have a challenge. This equation, y squared is x cubed minus 2, is an example of an elliptic curve. So the reason that I wrote it in that format is that we traditionally write elliptic curves as y squared equals cubic in x. So it's cubic because the highest power of x there is a 3. So I've drawn this nice picture of it. I didn't feel like that was totally representative of what elliptic curves might look like if we draw pictures, so I drew some more for you. If you haven't thought about graphs of the form y squared equals something, you might like to go and play with that idea a little bit for yourself. It's kind of interesting. So you're kind of maybe used to thinking about y equals something. What about y squared equals something? It's quite interesting. You might think about what features of the graphs here are a consequence of that. So these are thinking about the real points here, whereas before we were thinking about the whole number solutions. That's where we found there are only 2. There's quite a lot to be discovered by thinking about complex solutions. So if you allow an x and y to be complex numbers, you end up with some exciting kind of donut torus type shape, because there are some extra dimensions, because each of the complex numbers is kind of 2 dimensions, and then you pick out a surface within it. It's all very exciting. It ties in with kind of topology. So this arithmetic geometry, which is all about these kind of rational points, integer points on these equations, and so on. And elliptic curves are utterly crucial in Andrew Wiles's proof of Fermat's last theorem. So the Taniyama-Shimura conjecture that he proved was for a particular type of, a particular family of elliptic curves, and he proved that they all had certain properties. So I'm a long way off explaining to you how his proof goes, because it's really hard. But these elliptic curves are fundamental objects, but they're also kind of interesting in themselves. There's a lot of structure to explore there. They link up with algebra, geometry, number theory. They all kind of come together here. Okay, let me tell you why this is all really hard. So David Hilbert was a leading German mathematician, end of the 19th, beginning of the 20th century. And every 4 years, the mathematical community gets together at what's called the International Congress of Mathematicians. And everybody gets together, and there are sort of talks by fantastic mathematicians saying, well, this is what I've been doing in my research recently, and people exchange ideas, and they present prizes, and there's all sorts of things. At the International Congress in 1900, Hilbert announced these problems. He made his list of problems that they were kind of like a challenge to the mathematical community. These are the problems I think are really important. Here's 23 of them. And the one that's relevant for us here is Hilbert's 10th problem. So some of Hilbert's problems have been solved. Some of them have not yet been solved. So, when you've sorted out the other little loose ends I've left you to think about on the bus back, or maybe that'll take you to tomorrow, go and look up Hilbert's 23 problems and pick one to work on. That'll keep you busy for a while. And when you've got a solution, I will be the first to congratulate you, because that would be terrific. Especially if it's Riemann hypothesis. I'm very interested in the Riemann hypothesis. Coefficients, the numbers are whole numbers, and you want whole number solutions. So they're exactly the kinds of things that we've been talking about today, okay? So that's just deciphering that. So any number of variables, we want whole number solutions. Everything in sight is a whole number. And what Hilbert wanted in his problem was to come up with a kind of algorithm, a process that a computer could run. He wasn't saying that in 1900, but that's how we might now think about it, that would decide whether this equation has whole number solutions. So not even as difficult as the problem I gave you right at the beginning of how many are there, but just are there any solutions or no solutions? And this algorithm has to you feed in your equation, the computer whirs and clunks a bit, and crucially, after a finite amount of time, comes back and says, yes, it's got integer solutions, or no, it hasn't. Okay, so that's what Hilbert wanted. Hilbert very much had this agenda that we would find out the answers to this, that you can answer all mathematical problems. By the 1930s, it was becoming clear that that's just not true. I don't mean not true in some sort of vague philosophical sense. I mean not true in a provable mathematical sense. So there's this extraordinary mathematician, Gödel, who came along and turned it all upside down and said, well, hang on a minute. So people just started to think, well, is it even possible to come up with this algorithm, this process that Hilbert wants? And one of the first people to make progress on this was Julia Robinson, who's a really interesting mathematician and not enormously famous, but should be more famous, I think. It's a really interesting story. So things like she married a mathematician, and because he had a job in the department, she wasn't allowed a job as well, because there were rules saying they couldn't both be employed. After she'd kind of solved this world-famous problem, they did eventually decide they'd give her a job. So in 1952, she made a breakthrough that wasn't immediately related to Hilbert's 10th problem, but wrote this paper that would turn out to be enormously relevant. So she was thinking about something slightly different. And then in 1960, she got this draft of a paper by two other mathematicians, Davis and Putnam. And she realized that if they combined her work with their work, they'd have made a lot of progress on this problem of showing that, in fact, there isn't such a process. And then so they wrote up this paper in 1961, and they said, well, here's where we're at. In 1970, this very young Russian mathematician, Matyasevich, managed to fill in the gap they were missing. And having seen how he did that, Julia Robinson realized that, in fact, she'd sort of been quite close 20 years earlier. But you have to look at the problem the right way. You have to have the right ideas in the right order. So it's this kind of collaboration showed there is no computer program that is guaranteed to decide in a finite amount of time, yes, this Diophantine equation has integer solutions. No, it doesn't. Now, depending on your perspective, that's devastating or fantastic. I mean, it means that different Diophantine equations are really hard, right? You can't just use a computer to decide, yes, there's a solution, no, there isn't. So that's great, because it means there are lots of Diophantine equations out there to study. So the tools that Andrew Wiles used for studying Fermat's last theorem, that equation, people are developing to tackle more equations. There are other equations out there that we still just don't have the tools to begin to understand. And, it would be great if some of you got involved in sorting that out. So my question for you is, which Diophantine equations will you tackle next? Thank you very much.